Hi, this is the start of a lecture discussing adders, and to understand the topic of adders, we will address adders in multiple dimensions, if you will. Um, so we will first talk about adding one bit, two numbers or two binary numbers, where each is one bit. So we're going to add, for example, 1 plus 1 plus 1. These are just in binary numbers, one bit, and we'll find out their result. And then, and then, um, uh, so you can say 2 or 3 actually, but the reason we say 2 or 3, because you will see that later on that the first one is always a carry out of the previous bit position. Then we will add two numbers, multi-bit multi multi-bit multi-bit numbers. For example, I'm sorry, 1011 plus 0110. So these are multi-bits, two numbers. And then we will add uh, multiple multiple multi-bits. Okay, so we'll add 101010000001. So these are more than two numbers. Each has more than one bit. Okay, and we'll start by addressing the single bit or one bit number in the next one or two lectures. All right, so that we clear this out. Okay, so let's okay, so in terms of one bit number, so we're adding one bit number, so we're adding that's 1 plus 1, for example. Okay, so we know that in this case that we have the result as 1 and 0. We call the very first number here as we call it the sum, and the second number we call it the carry, as you recall from your logic class. Okay, and we are adding here two numbers. We can add three numbers, for instance. So for example, I can add 1 plus 1 plus 1. Okay, all single bits here. Notice that every one of them is single bit. Okay, and the answer will be a sum of a 1 and a carry out of a 1. So in this case, you can see that this is the sum. Okay, and this is the carry out. Okay, now it is important to notice that the weight, the weight, the binary weight of the sum is of equivalent to those we are adding, but the binary weight of the carryout is higher. So you can say that these are the units. This is a unit, 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 unit. What do we mean by unit? The weight is 2 to the 0. But here we can say this is tens. The weight is 2 to the 1. Okay, and that's why when we add 1 plus 1 plus 1, okay, if I want to evaluate this, it will be 1 times 2 to the 0 plus 1 times 2 to the 1. This is actually equals 3. Okay, so the weight of the sum, the weight of the sum, which is this one here, is of equivalent to the weights of the bits that we are adding. The weight of the carry is higher. Okay, now, so let's address one more thing here, is that what is the hardware that adds these two numbers? As we have taken from logic class, is that if I'm adding two numbers, 1 plus 1, then and the output is sum and a carry, then there is a special hardware that does that. We call it half adder. And half adder has two inputs, A and B, each is one bit, and two outputs, sum and carry. Okay, And we will see very shortly the truth table for this one. And actually, the truth table is very simple. If you have A, B, right, and the permutation and combination for this is very simple. So you have here the carry and the sum. Okay. So now you can see that A can be 0, 0, and B can be 0, 0, 0, 1, 1, 0, 1, 1. And in this case, the sum is here is 0, carry 0, 1, 0, 1, 0, 1, 0. So notice that here the value here, if this is the 1, the value here is 1, 1, and this is 2. We are adding two ones here, so the value here, the output is 2. So very simple truth table. But if I'm adding 3 bits of ones, okay, so it's three bits of ones. So to add this, we have studied in logic class a special hardware for this, which is we call it the full adder. Okay, so A, B, C, and this the output is as sum and carry. And the difference between the half adder and the full adder is that the full adder adds 3 bits, while the half adder adds just 2 bits. Now, if you look at the truth table for this thing, so this is A, B, C, and the sum and the carry out. Whoops, sorry. So this is carry out, and so this is C out and sum. Okay, so we this is the truth table here. Okay, so let's see if I can get this thing. Okay, and now so have this is a 0, 0, 0, and if I'm adding 0, 0, 0, the sum is 0 and the carry out is 0. If I'm adding 0, 0, 1 or 0, 1, 0, okay, see 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So if I'm adding just 1, 1, so the output will be 0, 1. So is this case 0, 1, and so is this case 0, 1, right? But if I'm adding two ones, then the carry is a 1 and the sum is a 0, right? And so is this case, and so is this case. If I'm adding three ones, the sum is a 1 and the carry out is a 1. Okay, so this is kind of a review what we have done in earlier class when we studied half adder and full adder. Let's come back to our class here. Okay, so in our class here, we'll study the single bit here. Oops, sorry. Okay, so the single bit. As we have seen here, this is the half adder, this is the full adder. The half adder has two inputs, A, B, each is a single bit, and the output is a sum and C out. Okay, and this is the truth table that we have derived earlier. Okay, and this is the output values. Okay, now you can see here the full adder. The full adder is has 1, 2, 3 inputs, and the outputs is the sum and the carry. Okay, so you can see the truth table here. This is A, B, C. These are the inputs, and these are the combination of the inputs, and these are the outputs here, the sum and the carry out. So you can see that when I have three zeros, as we have derived earlier, and all the way to the end of the cases. Now, one thing is interesting here is that if you derive the logic value for the sum for the half adder, then it turned out that the sum is the exclusive OR of A and B. If you look, you can verify this through K-map. And if you look at the C out, it's the ANDing of A and B. This is for the half adder. So is the exclusive OR of A and B is the value of the sum, and the ending of the A and B is the value of the C out. Now, for the full adder, though, the sum is the exclusive OR of A, B, and I'm sorry, exclusive OR A, exclusive OR B, exclusive OR C. And the C out is called the majority function. The majority function, what do we mean by the majority function? Well, here is what we mean by the majority function. Let's choose this color here. the majority function equals this value. If you look at the K-map, we can derive this as A, B, or B, C, or A, C. Okay, that's from the K-map. All right. Someone might say, well, how is that the K-map? So if you draw the K-map, and I'm talking about this here for C out. If you draw the K-map, okay, so this is basically A 01, B C out 00011110. You will see that you will see that this is here 1 1 1 1. So you can derive the minimize the three terms using the K-map, which are right here. Okay, these are the three maps from the K-map. Okay, now interestingly enough, we can prove that these two expression are equivalent, and which is this is the inverted expression. Okay, so we kind of if you apply De Morgan law, you can prove that this is the same as this one. So AB or BC or AC is equivalent to the inversion of A prime B prime or C prime ANDed with A prime or B prime inversion. Okay, so this is the kind of the logic. So now let's talk about this majority function here. When they say majority function here, okay, so let's okay. Um, majority function. So the majority function here means what? The majority function, which is this C out here, it means that the output C out is we'll see what is the majority of the inputs. Here, the majority of the inputs are zeros, then the C out is a zero. The majority of the bits is what here? Is a zero, still zero. The majority of the bits is zero, zero. The majority of the bits value is what? A 1, then becomes a 1 because I have two ones here. How about the majority of the bits here is what? Is 0. All right. How about here? What's the majority of the bits? It's a 1. So that's why they call the cout is a majority. It will follow the majority of the values of the bits. Okay. All right. Now we go here and we investigate just implementing the adder using simple logic. So what we did, we said the sum is what? The sum equals A exclusive or B, right? Exclusive or C. So we implement this using and this is equals A B C or A prime B C or A uh, B prime C or A B C prime. Okay, so this if you expand the XOR, this is what you get. So we go ahead and implement it like so in and this. Notice that here we are implementing this using an AND and an inverter, and then and here I have an OR and inverter. We don't have an OR gate or an AND gate in digital circuits. We have to implement NOR and then we invert it to get an OR, an AND, and we invert it to get the AND gate. So you can see that if we count those gates and or we count the number of transistors as we have learned in DIC, we'll see that every NAND here is a 6 transistor, okay, and every inverter is 2. All right, so we need that much of logic to implement what? To implement the sum, okay, that much of circuits. Okay, how about the carry out? The carry out, we said it's A, B, or B, C, or A, C. So we implement it in this circuit right here. Okay. All right, and you can see two levels, one level for the and one level for the or. Okay, and we need these, since we need A prime and B prime and C prime, we need these inverters. You add everything together. If you add all these, okay, so uh, three NAND, it's 6 transistors. So if you want to count number of transistors, we know that the NAND gate 3 inputs is 6 transistors. So the inverter is 2. The three the let's see the three input this one here is 4 input NOR gate, 8 transistor, an inverter. And then for the carry out, you need 2 levels of to implement an AND, an NAND, and an inverter for plus 2 for every one of those. And then the NOR gate 3 plus 2, 6 plus 6 transistor plus 2 transistor, and then the inversion for these inverter. You add everything and you get a total of 74 transistors to implement what? To implement a full adder. So the full adder takes without any optimization 72 transistors. That is a lot. In the next few slides, what we'll try to attempt is we would like to minimize this number as much as one. This is no good. 72 transistor is no good. What we are trying to attempt here is to minimize the number of transistors required to implement full adder, because the adder is so basic in digital design. So the adder is very fundamental. We need to optimize it to the least number of transistors, because least number of transistors means least area, least power, least energy, and that's why we need to optimize it as much as we can. We need to squeeze the last transistor out of this thing so that we can optimize the design. Okay, so let's take a look at what we can do in the next couple of slides. Okay, so recall this number 72. Can we do better? Okay, we'll leave this slide later on. We'll discuss it. Okay, here is one suggestion, and this suggestion, what it does is it really uses 30 or requires 32 transistor using complex gates. So this gate is a complex gate, complex CMOS, as we have studied in the IC. So basically what we are doing, we have a large gate to implement C out and a large gate to implement the sum. Okay, and notice here, the interesting is that we are implementing the sum as X A XOR X NOR inversion. So by having the output generated already as inverted, we don't need the inverter here, because this inversion is implemented automatically by the fact CMOS is what? CMOS is it has an inversion output. So this inversion comes free from CMOS. But notice here I have A XOR X NOR. So why X NOR? Well, because this inversion, when it gets inside, it flips the XNOR to XOR. Okay, and I know that the sum is what? That the sum is A XOR B X or C. Okay, so we can probably take this to the whiteboard for a second here. So let's go to the whiteboard here and say. So basically what they have done is that they saying sum equals, we are saying A XOR B XOR C, right? So when we did, we add double inversions. So here is 1 and 2. We didn't do anything. This is bad. So now we keep one of them, which is this one, and then we introduce the lower inversion. This is A XOR B X NOR C. Okay, and that's what we have in the slide, but they are saying that A X NOR XOR B X NOR C, and then you have the inversion. So that's what we have in the slide. Okay, now how about C out here? Again, C out here is more of optimized expression. Okay, and as we can see that it's A B prime C C prime A prime or B prime. So this is an expression where also we can derive this expression. Oops, sorry. We can derive this expression uh, uh, with the K-map or logical optimization. Now you can see here what we have is, okay. So you can see here what we have is, if you take this and implement it with this complex gate. And here what they have done lots of sharing between these arcs. You can see here what they have done. They have tried to do a lot of sharing. Like for example, this transistor right here, this transistor is shared between this expression and this expression here. Okay, so is this transistor shared between here and here. So with sharing transistors between multiple branches, they were able to bring down the number of transistors. Okay, so let's now investigate a little more here into how they have done this. Okay, so to help us understand the circuit more, so we brought the circuit to the whiteboard, and for this circuit here, oops, let's not do that. Um, okay, for this circuit right here, we are going to look at um, if you see this implementation here, how what it implements the following function: s equals. So now you can read this arc here. Okay, so you can read this arc, which is this right here, which is basically C prime, C, A prime, B, C, okay, or, okay, I can see that there is another arc here where it goes through the C, which is, which is, it is A, B prime C, A, B prime C plus, and I can start from this branch here now, which is A, B, C prime, C prime, and I can see this branch right here where it is A prime, B prime, C prime. Now all of this, by the way, is prime, and it turned out this is here, this function here is equal to S equal A. Well, I'm sorry, it is A XOR B XOR C prime, and this is exactly this expression right here. Okay, now let's try with the we'll see in a second input pattern here. So let's get this expression and take a look at the C out here. Okay, so the C out. All right, so the C out. Let's try to see what the C out implements. Okay, so the C out here says the C out says that this is equal C out equals what? It is equal to A prime, B prime plus C prime. So I'm gonna introduce it to the brackets. So A prime C prime plus B prime C prime, all under prime. So now apply De Morgan's law. So De Morgan's law says what? It says A prime B prime, okay, prime, ended with A prime C prime, ended with B prime C prime, right? Now open the brackets under De Morgan. A or B ended with A or C ended with B or C, and if you do open the brackets at the end, you will get A, B, or B, C, or A, C, which is the expression for C out, which is actually the majority function as we have seen it earlier for A, B, C. Okay, so this is exactly the okay. So now you can see how can we double check here and read what's being implemented at this point. Okay, let's see. So this is here what? This is A prime ended with B prime, or from here to here C prime ended with A or A prime or B prime. Okay, all is primed. This is exactly this expression here and which is equal to the carry out expression. Okay, now let's try a few values here. How about if we say assume a equals 1, b equals 0, and c equals 0. Let's see what's the output. Now I know that the sum should be 1, the carry should be 0. Okay, let's try that. Okay, so if I have this input pattern, okay, this input pattern here. So if I have here, let's get the red color here. Okay, so I know that the C is what? The C here is 1, and the B here is 0. The C here, the A here is 1, right? The A here is 0. The B here is 0, and the C is 0. Okay, the C here is C prime equal be a 1, and C here is 0. The B here is 0, and this is 0, and the A is 1, 0, and here it will be 1. Okay, you can see clearly I have a path here to VDD, which will, and I don't have any path to ground, which will pull C1 to high, and will I'm sorry, to the sum to high, which makes the sum equals high, which makes the sum equals 1. Okay, through this path right here. Okay, how about the carry? Well, let's see. A prime is 0, B prime is 1, and C prime is 1. I can see there is a path all the way to ground that goes and makes C out equals low, which is explain why C will get a value of a 0. The C out will a value of a 0. So the output will be discharged through this transistor and this transistor. So this is a circuit analysis, right, that we do rigorously for these type of adders. We need to understand the values of every input pattern. We need to understand how the carry out is implemented, when we need to understand how the sum is implemented. Okay, all right. Well, thank you very much for this lecture, and we'll continue discussing the adders in the next coming lectures.